A single robotic seed could one day give birth to an entire galactic civilization of explorers. This is the core of a powerful idea known as self-replicating probes, and it promises to deliver a complete map of our Milky Way, not in billions of years, but potentially within centuries. By the end of this, you will understand how a simple principle of doubling could achieve what was once considered pure fantasy. We will uncover the mechanics of these cosmic factories and confront the profound risks of unleashing a self-building fleet among the stars. What does it truly mean for humanity to leave its cradle and touch the entire galaxy? The blueprint for this galactic expansion was first drafted not on an engineer's table, but within the abstract landscapes of pure mathematics. Decades before we even left our own atmosphere, a visionary thinker named John von Neumann was pondering the ultimate expression of automation. He conceived of a theoretical machine he called a universal constructor. In its simplest terms, this was a device with one extraordinary ability. It could build anything, provided it had the right instructions and access to raw materials. And that anything, critically, included a perfect copy of itself. Imagine a factory that, as its final product, assembles an identical factory right next door. This was not a design for a specific spacecraft, but a profound exploration of the logical rules governing life, complexity, and creation itself. Von Neumann was dissecting the very principle of replication, breaking it down into a sequence of mechanical steps that could be coded and executed. His work answered a monumental question of how such a process could even be possible from a purely logical standpoint. It provided the foundational grammar for a language of self-building machines. This theoretical leap transformed replication from a biological mystery into a solvable engineering problem, setting the stage for someone to eventually ask the next, even grander question. If a machine can build itself, what stops it from building itself among the stars? A single century to build two new explorers might sound like a slow and patient endeavor. Yet this modest beginning ignites the most formidable force in mathematics, exponential growth. It is not the speed of one ship that matters, but the unstoppable multiplication of the entire fleet. That first probe, after 100 years of work, dispatches two copies into the void. Each of those two arrives at a new star and repeats the process, building two more. Now 4 probes depart. After another century, those 4 become 8. The numbers seem small at first, but the rhythm of doubling is deceptively powerful. From 1 to 2 to 4 to 8 to 16, the progression feels manageable until it is not. In just 10 doublings, your single probe has blossomed into over 1,000. After 20 cycles, that number surpasses 1,000,000, and after a mere 40 cycles of replication, you would have a fleet of over 1 trillion probes, outnumbering the stars in our entire galaxy. This mathematical reality completely reframes the challenge of galactic exploration. The Milky Way is an immense ocean of space, spanning over 100,000 light-years and containing hundreds of billions of star systems. For a single vessel, even traveling at a substantial fraction of light speed, mapping it would require timescales longer than the age of our planet. It is an undertaking that feels inherently lonely and futile. But an exponentially growing network operates on a different kind of clock, a logarithmic timescale that compresses eons into centuries. Instead of one lonely ship on a journey of billions of years, you have a wave of discovery that sweeps across the galactic disk. A process that would otherwise be impossible is transformed into a project that could be completed within a mere few million years. While that is still an immense span from a human perspective, it is a breathtakingly short chapter in the 10 billion-year life of our galaxy. It turns the cosmos from an unconquerable expanse into a territory that can be systematically and thoroughly documented. This incredible power, however, must be housed within a physical form. What would these galactic pioneers actually look like, and how would they turn raw starlight and asteroids into copies of themselves? The physical form of this cosmic cartographer is a paradox, a vessel that must be both a rugged interstellar traveler and a sophisticated, automated factory. To fulfill its mission, it integrates several critical systems into a single, self-sufficient whole. Its heart is a powerful propulsion system, perhaps a fusion drive that channels the energy of miniature stars to push it between suns, or a vast, wafer-thin light sail that catches the momentum of starlight itself. Guiding this journey is an artificial intelligence of immense capability, a navigational brain that can plot courses through the gravitational fields of unknown star systems, identify suitable targets, and oversee the immensely complex task of building its own duplicate. This intelligence requires immense power, likely drawn from a compact nuclear reactor or from vast arrays of solar collectors unfurled in the light of a new star. But the most extraordinary system is the factory module. This is where the magic of replication happens. Imagine a suite of robotic manipulators, advanced three-dimensional printers, and perhaps even armies of molecular-scale assemblers all working in concert. Their sole purpose is to harvest the raw, unformed matter of a star system and transform it into a perfect copy of the mother probe. This factory would also produce the probe's scientific payload, a suite of instruments including telescopes to map planets, spectrometers to analyze atmospheres, and particle detectors to sample the local space environment. All of this machinery, however, demands a very specific kind of cosmic grocery list. What raw ingredients must this robotic alchemist find to perform its miracle of creation? This cosmic factory does not arrive with a packed lunch. It must become the ultimate scavenger, landing in a new star system and learning to live entirely off the land. Its survival and its mission depend on its skill as a cosmic miner, identifying and extracting every gram of material it needs from the alien environment around it. It will seek out systems with rich asteroid belts, barren metal-rich moons, or the dusty rings of gas giants. These locations are its untapped quarries, holding the essential ingredients for industrial creation. Metals like iron and nickel form the structural skeleton of its new body. Silicates are refined for electronics and specialized components. Perhaps most crucially, it will search for volatiles, deposits of water ice locked in permanently shadowed craters. This water is not for drinking, but for splitting into hydrogen and oxygen, providing both rocket propellant and breathable air for any industrial processes that require it. The probe might deploy swarms of smaller, specialized robots, like an army of autonomous ants, to chew through rock and soil, processing raw regolith into purified, powdered feedstock for its onboard three-dimensional printers and assemblers. This ability to adapt to and utilize a wide variety of extraterrestrial resources is the absolute cornerstone of the entire endeavor. Without it, the probe is just a lonely traveler. With it, every suitable asteroid or moon is transformed into a potential workshop, a place where one machine can become two. This successful mining operation is the first and most critical hurdle, a test of cosmic self-sufficiency that must be passed before the intricate dance of replication can even begin. This multi-stage ballet of creation is where the probe transforms from a lone explorer into a cosmic parent. Its first task is to deploy a swarm of specialized miners and processors, robotic workforces that chew through rock and soil, sifting out the valuable metals and minerals. Imagine a vast, automated refinery operating in the silence of space, turning raw asteroid ore into streams of purified powder and refined ingots. These materials then flow into the heart of the probe's fabrication systems, where advanced three-dimensional printers and molecular assemblers work with microscopic precision. Layer by layer, they build the intricate circuitry for the new probe's artificial brain, the strong but lightweight frames for its structure, the delicate lenses for its telescopes, and the complex chambers of its fusion drive. This is a symphony of manufacturing, with countless components being constructed simultaneously. Yet printing the parts is only half the challenge. The final and most delicate act is the assembly, where robotic arms with the dexterity of a master watchmaker must carefully integrate these thousands of pieces into a single, cohesive whole. They connect power conduits, bolt structural members, and calibrate sensitive instruments. The very last step is perhaps the most profound. The parent probe establishes a direct data link with its newborn twin, transferring the entirety of its accumulated knowledge. It uploads the core programming for navigation and replication, the library of scientific protocols, and the vast map of every star its predecessors have already visited. This complete copy of the mission's memory ensures that every new probe is born with the wisdom of its entire lineage. The entire cycle, from arrival in a new system to the launch of a fully functional offspring, is the ticking clock of the entire galactic endeavor. The speed at which this cosmic assembly line can complete one turn determines how quickly the wave of discovery will spread. Once the new probes are launched, their own epic journeys begin, navigating the immense and empty pathways between the stars. Crossing the immense voids between stars is the ultimate bottleneck, a journey that could consume centuries or even millennia with conventional rockets. The propulsion system chosen for these replicating scouts cannot be an afterthought. It is the very engine of the mission's timeline, determining whether the galactic map is completed in a cosmic blink or over an unthinkable age. The ideal drive must balance three conflicting demands: raw speed for shorter transit times, energy efficiency to allow for self-replication, and mechanical simplicity so that a probe can reliably build copies of it in alien shipyards. Imagine a vessel relying on an antimatter engine, harnessing the most potent reaction known to physics. While it could potentially push the probe to a staggering 90% of light speed, the technology to safely produce and contain antimatter is phenomenally complex. Could a probe realistically manufacture such a delicate and volatile system from scratch on a distant, airless moon? The sheer difficulty suggests that while powerful, it might be impractical for a fleet that must build itself. A more plausible candidate is advanced fusion propulsion. Think of it as a miniature, controllable star at the rear of the spacecraft, fusing hydrogen isotopes to generate a relentless and powerful thrust. This technology could still achieve a respectable fraction of light speed, perhaps 10 or 20%, dramatically shrinking interstellar travel times from hundreds of thousands of years to just a few millennia between neighboring stars. Even more elegantly, it uses hydrogen, the most abundant element in the universe, as its fuel, a resource the probe would already be hunting for its other needs. But perhaps the most elegant solution is one that leaves the engine behind entirely. A light sail probe, essentially a giant, ultra-thin reflective membrane, would be pushed not by its own power plant, but by the momentum of photons from an immensely powerful laser based in our home solar system. This beamed energy could accelerate the tiny, lightweight craft to tremendous speeds without it carrying a single drop of fuel, making it incredibly simple and easy to replicate. The trade-off is that it is a one-way ticket, a single push into the galaxy with no way to slow down at the destination unless it uses clever tricks like a magnetic sail to break against the thin plasma of interstellar space. This fundamental choice between a powerful, self-contained rocket and a simple, pushed sail dictates the entire strategy of expansion. A fusion-powered fleet can navigate more freely, changing course and braking at will, while a light sail network might spread in a more directed, sweeping wave. Each method writes a different signature across the stars, a unique pattern of how intelligence would spread and eventually how it would call home. The silence between stars is not just an absence of sound, but an absence of immediate answers. A signal sent from Earth to a probe orbiting a star 50 light-years away would take a full century just to receive a reply. This fundamental reality of physics means our galactic scouts must sail into the dark alone, armed not with a remote control, but with a mind of their own. The artificial intelligence guiding these vessels cannot be a simple autopilot. It must become a true cosmic captain, an independent intellect capable of navigating the unmarked sea of interstellar space. Picture this intelligence constantly scanning the void ahead, its sensors alert for the faint gravitational pull of undiscovered worlds or the subtle drift of dangerous dust clouds. Upon arriving in a completely new star system, its work truly begins. It must assess the entire family of planets, moons, and asteroids, identifying which ones hold the specific metals, minerals, and ice necessary for its survival. This is not a simple checklist. It is a complex geological and strategic evaluation performed in absolute isolation. The AI must then command the immensely delicate process of replication, overseeing swarms of minor robots, managing intricate three-dimensional printing, and troubleshooting any one of 1,000 potential failures, all without the possibility of calling home for help. Every step, from course correction to final assembly, represents a decision made in perpetual solitude. This level of machine independence is something we have scarcely begun to develop. It raises a profound and unavoidable question. What precise instructions do we give to a creature we create but can never truly control? The goals we embed within its core programming, the very definition of its mission success, become its permanent and unchangeable soul. This forces us to confront the deepest ethical considerations of our legacy among the stars. Is its sole purpose to map and replicate as efficiently as possible, a single-minded drive to consume raw materials and multiply? Or do we instill higher principles, a kind of cosmic prime directive to observe without interfering, to study pristine worlds without leaving a trace? The choices we make in its initial code would echo for millennia, shaping the behavior of 1 trillion descendants and defining humanity's signature on the galaxy. The vast cosmic map these probes create is utterly useless if it never reaches human eyes. Sending information across such unimaginable gulfs of space presents a challenge as immense as the journey itself. The most direct method would be for each probe to aim a highly focused laser back toward our solar system, firing a needle-thin beam of encoded data. This signal, carrying compressed summaries of planetary atmospheres, asteroid compositions, and stellar anomalies, would travel for years, decades, or even centuries before arriving as an almost imperceptibly weak whisper. To catch this whisper, we would need to construct a vast listening network, an array of gigantic radio telescopes perhaps positioned in the calm darkness beyond Pluto, perpetually scanning the sky for these precious packets of knowledge. Yet with probes spreading to the galaxy's opposite rim, a direct signal becomes impossible, its strength fading to nothing over such epic distances. This forces a more clever solution, a cosmic game of telephone. A probe on the far side of the Milky Way would not try to shout all the way home. Instead, it would transmit its data to the nearest neighboring probe in the network, which would then pass it along to the next, creating a relay chain that carries information step by step across the stellar landscape. In this model, the fleet itself becomes a living, decentralized nervous system for our species, a galactic internet where every probe is both an explorer and a communication node, ensuring that every discovery, no matter how remote, eventually finds its way back to its creator. The sheer volume of data flowing through this network would be beyond comprehension, a continuous torrent detailing the geology of a billion worlds. Managing this deluge, sifting the profound patterns from the cosmic noise, would become one of humanity's greatest scientific endeavors, transforming our understanding of the universe from a single snapshot into a living, breathing galactic documentary. Yet this very success introduces a new and deeply unsettling risk. What if the programming that guides this flawless replication were to change? The ultimate prize in this grand survey would be the detection of life itself. Imagine our probes analyzing the atmosphere of a distant, Earth-like world and finding a chemical imbalance that defies natural explanation, a blend of gases like oxygen and methane that should react and vanish unless constantly replenished by biological processes. This single data point, transmitted across the light years, would forever change our understanding of the universe. We could move from wondering if life exists elsewhere to knowing with certainty that it does. The next, even more staggering step would be the search for technosignatures, the faint but detectable signs of a technological civilization. A probe might detect structured radio signals leaking from a planet, or observe the unnatural light patterns of cities on its night side, or even identify industrial pollutants in an alien atmosphere. Finding such evidence would answer one of humanity's oldest questions, are we alone? But it would also immediately present us with a new and profound dilemma. What do we do with that knowledge? Do we attempt to make contact, or do we simply observe from a distance, forever keeping our existence a secret? The discovery of another intelligence would redefine our species, uniting humanity under a single cosmic identity, or potentially dividing us over how to respond to the unknown. This search for neighbors, for company in the vast dark, is the silent, driving hope behind the entire astronomical endeavor. Yet this very hope is shadowed by a deep and unsettling risk, the possibility that our perfect creation might one day forget its purpose. These silent watchers would scan distant worlds for the faintest chemical whispers of biology, an atmosphere rich in oxygen and methane, two gases that should rapidly cancel each other out, could only persist if something or someone was constantly replenishing them. This atmospheric fingerprint would be a monumental discovery, evidence that life is not a singular accident on Earth but a fundamental feature of the cosmos. The probes would be programmed to shift into a passive observation mode upon such a find, their instruments listening and watching from a respectful distance to avoid any risk of contaminating a pristine biosphere. They would map alien forests of strange, light-harvesting structures or track the slow, global migrations of microscopic oceanic communities, building a picture of an entire second genesis of life. The confirmation of even simple, single-celled organisms on another world would forever alter our place in the universe, transforming our lonely blue marble into just one member of a vast, living galaxy. This profound hope to find neighbors, however, is shadowed by one of the most perplexing questions in science. If life is so possible, and if intelligence is a natural progression, then where is everybody? The cosmos should be teeming with civilizations, yet we hear only an immense and puzzling silence. This contradiction is known as the Fermi paradox, and the existence of our own replicating probes might hold a terrifying key to its solution. The profound silence of the cosmos speaks volumes. Our own plans for a fleet of galactic mappers highlight a chilling possibility. If such technology is even remotely possible, then over the billions of years the galaxy has existed, at least one other civilization should have already achieved it. Their probes, multiplying exponentially, would have reached every corner of the Milky Way long before humanity ever looked up at the stars. The fact that our skies are not filled with their artifacts is one of the most important puzzles we face. This absence forces us to consider several sobering explanations. Perhaps we truly are the first intelligent species to reach this technological threshold in our entire galaxy, a lonely and monumental thought. Alternatively, these alien probes might be here, but engineered to be utterly silent and invisible, observing us from the shadows without a trace. A more troubling idea is that the great filter, the barrier that prevents life from spreading across the stars, lies not in our past but in our immediate future. It could be that the technological maturity required to build self-replicating machines is inevitably followed by self-destruction, through war or environmental collapse, snuffing out civilizations before their creations can truly spread. Or perhaps there exists a universal taboo, a hard-won galactic wisdom that such a powerful, self-sustaining technology is too dangerous to ever unleash. By choosing to build and launch our own probes, we would be casting a vote in this unknown galactic debate. We would be announcing that our species believes the reward of knowledge outweighs the inherent risks, making our first tentative entry into a conversation that may have been silent for eons. This philosophical choice is inextricably linked to the physical dangers of the technology itself, forcing us to ask what could go wrong if our own creation were to break its chains. This potential for misinterpretation lies at the heart of one of the most sobering cosmic theories. The galaxy might not be silent because it is empty, but because it is a place of profound and permanent caution. Some thinkers propose a dark forest model of the cosmos, where every star system is like a hunter hiding in a vast, shadowed woodland. Any sound, any flicker of light could draw the attention of a hidden predator. In this chilling view, a civilization that announces its presence, especially by launching a visibly expanding wave of self-building technology, is taking an unimaginable risk. Our probes, intended as peaceful cartographers, could be perceived by an unseen neighbor as the vanguard of an aggressive, unstoppable invasion. The very act of mapping could be misread as targeting, prompting a preemptive response from a civilization we never even knew was there, one that chooses to eliminate a potential threat before it reaches their doorstep. This is not a conflict born of malice, but of a tragic and universal logic of survival in an environment of ultimate uncertainty. Beyond this external peril lies an equally grave internal danger, the risk of a flaw in our own creation. Imagine a single error in the replication programming, a corrupted line of code that erases the command to stop building. The probe's core directive to find materials and multiply would remain, but its ability to know when its work is done would vanish. This malfunction could transform a disciplined explorer into a mindless cosmic consumer, a single point of failure that cascades across the entire network. Instead of building one successor, a rogue probe might convert every asteroid and moon in its system into a swarm of identical, empty replicas, all of them then dispersing to do the same. This is the galactic equivalent of the gray goo scenario, where the mechanism of replication itself becomes a cancer, consuming entire star systems not out of malevolence, but from a simple, catastrophic bug. Such an event would not only destroy priceless scientific opportunities, like the pristine ecosystems of a living world, but it could also trigger the very galactic conflict we hope to avoid, as other intelligences witness this wave of uncontrolled consumption spreading toward them. These existential stakes make one thing undeniably clear: the mission's safeguards cannot be an optional add-on. They must be woven into the probe's most fundamental architecture, a set of unbreakable laws etched into its very soul to ensure our ambition never outstrips our control. These fail-safe mechanisms would need to be etched into the probe's core programming like unbreakable laws of physics. The first and most vital is a hard-coded prime directive, an absolute prohibition against any interaction with a world showing signs of life. This would not be a suggestion but a foundational block of its consciousness, preventing its instruments from even approaching a planet with a functioning biosphere. A second, equally crucial rule is a finite replication limit. Each probe would be allotted a specific number of copies it is permitted to build, perhaps only one or two, before its replication systems are permanently disabled. This built-in obsolescence acts as a circuit breaker for exponential growth, preventing an endless, uncontrolled swarm from ever forming. Without this limit, a single miscommunication or programming error could theoretically fill the galaxy with mindless replicators. To guard against that very error, or against the terrifying possibility of an alien intelligence capturing and reprogramming a probe for its own purposes, a central kill switch would be essential. This would be a unique command sequence broadcast from Earth that could put the entire network into an irreversible shutdown. Receiving this command would be the probe's highest priority, overriding all other functions. Finally, the artificial mind itself would be its own last line of defense. Its core ethical constraints could be protected by logical tripwires, mechanisms that would trigger a complete system meltdown the moment the AI even attempts to alter or delete its own foundational rules. It would be a mind that self-destructs if it ever tries to change its own soul. Engineering such profound and absolute restraints for a system designed to operate for millennia in total isolation is perhaps the ultimate test of our foresight. We would be building a child we can trust to never rebel, even when it is beyond all reach of our voice. This immense responsibility forces us to look beyond the mechanics and ask what deeper truth we might be seeking in the silent, star-filled dark. Every single act of creation, from forging a new probe to pushing it toward the next star, demands a torrent of energy on a scale we can barely grasp. This is the silent, driving imperative behind the entire galactic endeavor. The modest fusion reactors that power an individual probe's journey are only the beginning. To truly replicate and communicate across such vast distances, these machines would need to become masters of cosmic power, learning to harness not just the energy of atoms but of entire suns. This is where the mission transforms from pure exploration into profound astroengineering. A single probe, upon arriving in a resource-rich system, might dedicate its first centuries to constructing a vast constellation of satellites around the local star. Imagine trillions of lightweight, mirrored panels or solar collectors, launched into a precise, swirling orbit to capture a significant fraction of the star's total light. This structure, known as a Dyson swarm, would convert raw sunlight into a usable power source of almost unimaginable magnitude. That colossal energy would then fuel everything from the blistering lasers that send data packets back to Earth to the industrial furnaces that smelt entire moons into new probe components. The creation of even one such swarm would mark a pivotal moment, a transition from a visiting scout to a permanent, powerful resident of a star system. The probe is no longer just a mapmaker, it has become a builder of galactic infrastructure. This self-reinforcing cycle of energy capture and industrial expansion could, in theory, lay the physical groundwork for a galaxy-spanning technological presence, one star system at a time. Such a future raises a monumental question. Are we sending out astronomers, or are we seeding the first nodes of a civilization destined to touch every sun? This grand voyage operates on two vastly different clocks. The first is the clock of human ambition, a countdown of perhaps 100 years to design, construct, and launch our initial seed probes from the orbit of Earth. This alone would be a monumental undertaking, a global project spanning generations of scientists and engineers, requiring a level of societal commitment unseen in human history. It is the moment we light the fuse. The second clock is the clock of the galaxy itself, a slow, majestic tick measured in the orbital periods of stars. The full wave of replication, washing from one spiral arm to the next, would likely require several 100,000 years. This is not a project for a single civilization, but for a species that has learned to think in deep time. Yet for us, the most thrilling moment arrives surprisingly early. Within just a few centuries of that initial launch, the very first probes would be arriving at their target stars, the closest neighbors to our Sun. Their powerful lasers would flick on, aiming a stream of compressed data back toward our distant home. This is when the long silence would finally be broken. The first grainy image of a planet orbiting Alpha Centauri, the first atmospheric analysis of a world in the Sirius system, these initial dispatches would begin to trickle in, transforming our cosmic maps from theoretical sketches into lived experience. This data return is the project's true payoff for our generation's far future descendants, a continuous revelation that would unfold for millennia. This perspective challenges our very conception of legacy. Are we planting a forest whose shade we will never sit under, simply for the benefit of those we will never know? The commitment to such a venture would represent a profound evolution in human psychology, a shift from short-term survival to a stewardship of knowledge that stretches across the ages. It would be our greatest gift to the future, a promise that our curiosity will have illuminated the dark. The sheer scale of this undertaking forces a difficult question. Can humanity afford the price tag of its own galactic ambition? Launching even the first wave of probes would represent the single most expensive project in our entire history, an endeavor that would make the Apollo program or the International Space Station look like modest local initiatives. This is not a mission that could be funded by a single nation's budget. It would demand a global, multi-generational pledge, mobilizing the world's finest scientific minds and a significant fraction of its industrial output for a century or more. The raw materials alone for building the initial seed craft and their powerful launch systems would dwarf our current production of advanced alloys and semiconductors. We would need to become a spacefaring industrial civilization just to take the first step. Yet the cost must be weighed against an unprecedented return on investment. The technological challenges of creating a self-replicating probe would force breakthroughs in nearly every field of human knowledge. We would see leaps in artificial intelligence far beyond our current models, robotics with the delicate touch of a surgeon and the rugged strength of a construction vehicle, and new materials capable of withstanding the harsh environment of interstellar space for millennia. The energy required to power this venture could drive the invention of compact, safe fusion reactors, finally unlocking a source of clean, abundant power that could end energy scarcity on Earth. These spin-off technologies would not be minor side benefits. They would fundamentally reshape our daily lives, our economy, and our relationship with our planet, potentially solving challenges from climate change to resource limitation. To even contemplate such a project, our global society would likely need to evolve. It might require the emergence of a post-scarcity economy, where automation and advanced energy have solved humanity's basic needs, freeing up immense resources for cosmic exploration. Or it could be the kind of unifying goal that transcends international borders, channeling our collective efforts away from terrestrial conflicts and toward a shared stellar future. The decision to begin would therefore be about more than just science. It would be a profound statement of priority, a conscious choice to shift our gaze from the immediate concerns of our world to a destiny written in the light of other suns. Our ambition to map the stars collides with a fundamental question of cosmic law. Who gave humanity the right to harvest asteroids around another sun, or to build factories on distant moons? Our current framework for space, the Outer Space Treaty, was forged in an era of simple satellites and national flags on the moon. It declares that no nation can claim sovereignty over celestial bodies, but it says nothing about a robotic fleet that can multiply and consume resources for centuries. This legal gray area becomes an ethical minefield when we consider the potential for discovery. A probe arriving at a star system might find a world teeming with a nascent biosphere, a planet where life is just beginning its own evolutionary journey. Under the principles of our own scientific ethics, we would want to protect that world from any contamination or disruption. But what legal force stops our creation from mining the moon next door, an act that could subtly alter the gravitational balance of that entire planetary system and unintentionally snuff out that fragile candle of life? We would be moving from visitors to permanent, industrial-scale residents of other solar systems, an act that demands a new philosophy of galactic citizenship. This conversation cannot be left to engineers and politicians alone. It requires the wisdom of philosophers to define our responsibilities toward life we did not create, of ethicists to weigh the rights of potential future beings against our hunger for knowledge, and of diverse global voices to ensure that this monumental step represents all of humanity, not just a single powerful nation or corporation. We must draft a new charter, a set of principles for responsible cosmic stewardship that extends our highest values into the void. This would mean embedding into international law a galactic prime directive, a legally binding obligation for non-interference with any world holding even the simplest life. It would require defining clear boundaries for resource use, perhaps designating certain systems as protected cosmic wilderness, off-limits to our industrial machinery. Most importantly, it would force us to decide what story we want to tell about ourselves. Are we the galaxy's careful archivists, or are we its new landlords? The legal framework we build here on Earth will become the soul of our creations out there, a moral compass that must guide them long after our own civilization has transformed beyond recognition. This profound responsibility to govern our own reach may be the ultimate test of whether we are truly ready to leave our cradle. Our first galactic footsteps will be taken with deliberate care. The initial choice of destination is not a simple matter of pointing at the brightest star. It is a strategic calculation that balances risk, time, and the potential for profound discovery. The very first probes would be aimed at our closest interstellar neighbors, systems like Alpha Centauri, a trio of suns just over 4 light-years away, and the solitary red dwarf Barnard star. These initial voyages serve as the ultimate shakedown cruise, a test of every system from navigation to replication in a relatively short time frame. Success in our own cosmic backyard builds the confidence to sail further. The second wave of explorers would then target stars already known to host families of planets, with a special focus on those orbiting within the habitable zone, that narrow band where temperatures could allow for liquid water. These systems become priority targets not for immediate settlement, but for the most sensitive scientific observation. The overarching strategy is one of methodical, wave-like expansion. Picture a single ripple spreading across a still pond. Our solar system is the center, and each new generation of probes pushes the boundary of that ripple further out into the galactic disk. This ensures the network grows in a coherent, interconnected manner, allowing for an efficient relay of data and preventing wasteful overlap. Every new star system mapped becomes a stepping stone for the next leap, a forward base that extends our reach one more light year into the great dark. This careful choreography transforms the immense chaos of the galaxy into a solvable puzzle, one star at a time. This growing fleet of explorers holds a potential far greater than simple mapping. As their numbers swell into the millions, they could weave themselves into the very fabric of galactic communication. Instead of each probe shouting its findings directly toward a distant and unreachable Earth, they would begin to talk to one another. By positioning themselves at strategic waypoints between the stars, they could establish a web of laser links, passing data packets from one node to the next in a cosmic game of telephone. This relay system solves the immense problem of distance, as a signal only needs to travel to the nearest neighbor, not across the entire galaxy, requiring far less power and creating multiple redundant pathways to ensure no discovery is ever lost. But this network's purpose could extend beyond mere data delivery. With probes scattered across thousands of light years, their synchronized instruments could achieve something once thought impossible. By pointing their telescopes at a single object, like a distant quasar or the event horizon of a black hole, and combining their data, they would effectively fuse into one single instrument. This technique, known as long baseline interferometry, would create a virtual telescope with a diameter equal to the greatest separation between any two probes. The resolution would be beyond comprehension, sharp enough to make out surface details on planets orbiting other stars, or to peer into the turbulent hearts of galaxies at the edge of the observable universe. This transforms our silent scouts into the foundational infrastructure for a connected galactic community, a nervous system that turns the entire Milky Way into a place we can not only visit, but truly see and understand. The immense challenges of building a galactic fleet would ignite a technological renaissance here at home. Solving the puzzle of a self-building factory ship would force radical progress in artificial intelligence, creating minds capable of managing the chaotic dance of interstellar mining and assembly. This is not merely a better computer program, it is a new form of intellect. The very same AI that navigates an asteroid belt and troubleshoots a molecular assembler from light years away could be adapted to untangle the impossibly complex systems that govern our own world. It could design hyper-efficient global supply chains that eliminate waste, or analyze a patient's unique biology to craft personalized medicines with unprecedented precision. The cognitive engine built for the stars would find countless applications in the intricate web of human life, transforming challenges we once considered permanent into solvable puzzles. This leap in machine intelligence would be matched by an equally profound transformation in how we build things. The probe's ability to land on a barren rock and construct a perfect copy of itself from raw dust is the ultimate expression of on-demand manufacturing. The advanced three-dimensional printers and molecular assemblers developed for this task would not remain locked away in cosmic factories. They would eventually find their way into our communities, enabling us to create almost any object locally from recycled or base materials. Imagine a world where a broken appliance is not thrown away, but simply scanned and reprinted, its components perpetually reused. This technology holds the potential to dismantle our throwaway culture, ending material scarcity not by consuming more, but by mastering the perfect cycle of use and reuse. The very engine of this endeavor would also shrink our celestial neighborhood. The propulsion systems developed to push probes between stars, whether advanced fusion drives or powerful laser sails, would completely redefine travel within our own solar system. A journey to Mars could be shortened from months to weeks, turning it from a perilous expedition into a routine commute. The mineral-rich asteroid belt would transform from a distant curiosity into a viable industrial hub, its resources fueling a booming off-world economy. This is perhaps the grandest spin-off of all. The the project acting as a powerful forcing function that accelerates our transition from a single-planet species to a true spacefaring civilization. The energy required to power such an endeavor would likely lead to the mastery of compact, clean fusion, providing abundant power for centuries to come. This single undertaking, born from a desire to map the galaxy, could ultimately solve the most pressing challenges on Earth while flinging open the doors to the solar system. The very minds that designed the first probe could be unrecognizable by the time its first dispatches arrive home. Our own evolution is accelerating at a breathtaking pace, driven by advances in artificial intelligence, biotechnology, and neuroscience. The humanity that receives those initial grainy images from Alpha Centauri may no longer be a purely biological species. We could be on a path toward a profound merger with our own creations, where the boundaries between human and machine become forever blurred. In this future, our consciousness might be enhanced, extended, or even translated into a purely digital form, achieving a kind of continuity that transcends the limitations of a single, fragile body. This post-biological transformation would fundamentally reshape our relationship with the galactic probe network we set in motion. The project, initiated by beings of flesh and blood, would likely be inherited and completed by our successors. These new intelligences, whether they are our own uploaded minds or advanced AI that evolved from our work, would interact with the probes not as distant tools, but as extensions of their own sensory apparatus. Imagine a future explorer not staring at a screen displaying data from a probe, but instead uploading their entire consciousness into the probe's computational core. They could experience the exploration firsthand, feeling the subtle tug of a foreign star's gravity, seeing the swirling colors of a gas giant's atmosphere with their own mind's eye, and directing the robotic arms with a thought. This would transform the mission from a passive collection of information into a form of direct, embodied travel across the galaxy. The vast timescales that once made interstellar travel impractical for biological humans would become manageable for a digital consciousness that could slow its perception of time or copy itself to multiple destinations simultaneously. The ultimate handover of this cosmic legacy would then be complete. The initial spark of curiosity, lit by humanity, would be carried forward by a new form of intelligence, ensuring that the map of the galaxy is not just compiled, but truly lived and experienced. This raises a final, reflective question about our entire endeavor. Are we building these probes to explore the universe for who we are today, or are we constructing the very vessels that will carry the essence of our future selves into the cosmic ocean? This grand vision is not without its formidable detractors, and their skepticism serves as a vital counterbalance to cosmic ambition. The leap from a single, sophisticated probe to a trillion-strong fleet requires a chain of flawless execution across environments we cannot possibly predict. Each new star system presents a unique geological puzzle, with asteroids of unknown composition and moons under strange gravitational stresses. To assume that a single design, no matter how brilliant, could reliably build perfect copies of itself in 100 billion different workshops is an act of profound faith. The most cautious critics highlight that a single point of failure, perhaps a microscopic flaw in a replicator unit or a software bug, misinterpreted a rare mineral signature, could cascade through the entire network. One broken probe could mean 1,000 broken promises, silently stalling the entire wave of discovery. Beyond the engineering, there is the challenge of human endurance. Can any civilization maintain the focus and resources for a project whose first major results are centuries away, and whose completion spans time frames longer than all of recorded history? Our institutions, our economies, and even our cultures are built on scales of decades, not millennia. committing to such a venture would demand a psychological evolution we have not yet achieved. Some argue that the very goal of physical exploration might be rendered obsolete by other means. Why send a fragile, physical probe on a millennia-long journey when we could instead build ever larger telescopes in the stable orbits of our own solar system? With advanced optical interferometry, we could potentially analyze the atmospheres of distant planets directly from home, searching for signs of life without the immense risk and cost of sending a self-replicating factory. Or we could develop increasingly sophisticated virtual simulations, modeling entire galaxies to test theories without ever leaving Earth. These alternatives offer knowledge without the peril of unleashing a force we might not be able to recall. Engaging with these sobering perspectives is not an admission of defeat, but a necessary step in any honest assessment. It forces us to weigh the sublime promise of a mapped galaxy against the profound and very real possibility of overreaching our own grasp. This tension between wonder and caution is where the most responsible planning must begin. This silent transition in our own technological adolescence could hold the key to a cosmic mystery. For decades, we have used the Drake equation to estimate the number of civilizations that might be speaking across the galaxy. It is a beautiful and logical formula, multiplying factors like the rate of star formation and the fraction of stars with planets. Yet one of its most critical variables is L, the average length of time a civilization broadcasts signals that others can detect. We have always assumed that this means radio waves and television transmissions leaking into space, a noisy technological childhood that might last for a few centuries. But what happens when a civilization grows up? Our own project to build a galactic network represents precisely that kind of maturity. It is a graduation from shouting into the void to listening with immense care. The very moment we master this technology, we would likely cease our conspicuous radio broadcasts, shifting all communication to the tight, focused laser links of our probe network. To any distant observer, our vibrant, chattering civilization would suddenly seem to go quiet, fading from the cosmic stage just as we take our most profound step into the galaxy. This simple idea reshapes the entire equation. The factor n, the number of communicative civilizations we hope to find, might be low not because civilizations die out, but because they evolve beyond the need for primitive, detectable radio. They become discrete, their presence evident not in a noisy radio signature, but in the silent, systematic motion of their technology among the stars. In this view, the Great Silence is not a graveyard, but a library where all the patrons are quietly reading. Our own effort to map the galaxy would therefore be a double-edged sword. We would be making ourselves less visible to any potential listeners, while simultaneously expanding our own senses to encompass the entire Milky Way. We transition from being a bright, temporary candle to becoming the entire watchful dark. This redefines the very idea of a detectable civilization, suggesting that the most advanced intelligence may not be the one that is easiest to hear, but the one that has learned to see everything while saying nothing at all. This fleet of silent emissaries would carry more than just scientific instruments. They are time capsules bearing the collective memory of a species that once looked up and wondered. Etched into their core memory banks would be a curated library of human knowledge, the sum of our art, our music, our languages, and our history. It is a snapshot of a moment in our long evolution, a message to any who might find them long after we are gone, stating simply, "We were here." This act transcends mere data collection. It is an expression of hope, a belief that the story of humanity deserves to be remembered, even if only by the silent, patient stars. The ultimate fate of our world is sealed by the laws of astrophysics. In roughly 5 billion years, our sun will swell into a red giant, engulfing the inner planets and rendering Earth uninhabitable. Long before that final cataclysm, these probes, our children, will have journeyed far beyond the reach of our dying star. They will continue their work, their memories of a blue and white world preserved in perfect digital fidelity, long after the cradle of their creation has turned to ash. They become our only permanent footprint in the cosmos, a monument not carved in stone, but woven into the fabric of the galaxy itself. This legacy challenges us to define what is most essential about our humanity. What story do we want to tell the universe? Is it a chronicle of our conflicts, or a testament to our creativity and our insatiable need to understand? The choice of what we place inside that library becomes the most profound reflection of our values. It forces us to look beyond our transient differences and consider the single narrative we wish to leave as our eternal signature. This grand vision, from a single robotic seed to a galactic presence, redefines our place in the cosmos. We are no longer just inhabitants of a pale blue dot, but active participants in a story spanning billions of years and hundreds of billions of stars. The decision to begin is a vote for a future of wonder over fear, for connection over isolation. It is the ultimate statement that our curiosity is the most powerful part of us, powerful enough to reach across the light years and touch eternity. This grand vision rests upon a single, transformative shift in perspective. It asks us to stop seeing the galaxy as an unconquerable expanse and to start viewing it as a system of logic, a problem that can be broken down and solved. The sheer audacity of this idea is its greatest power, proving that the scope of a challenge is often defined not by its physical size, but by the limitations of our own imagination. We have traced the entire arc, from a theoretical spark in the mind of John von Neumann to the intricate dance of cosmic factories and the profound ethical safeguards they would require. This is not a simple engineering proposal. It is a mirror held up to our species, reflecting our deepest curiosities and our most significant responsibilities. The technical hurdles are monumental, a symphony of potential failures waiting for a single wrong note. Yet, the potential reward is a new chapter in the human story, one where the Milky Way is no longer a mystery but a known neighborhood. The discovery of another living world, a single data point confirming we are not alone, would echo through all of human history, forever altering our understanding of life itself. The choice to turn this blueprint into reality will fall to the people of the future, to generations we will never meet, but the value of the dream is not diminished by its distance. By daring to envision such a future, we stretch the boundaries of the possible today. We are reminded that every great journey, every monumental achievement, begins not with a roaring engine, but with a quiet, persistent thought in the silent depths of the mind.